So I'm Sergey, and this is Applied Depth Sensing. In this talk, I'm going to give you some motivation for using depth cameras in robotics. We're going to go over the landscape of depth sensing technologies that are available right now, and we'll finish with some real-world application and the raffle. So before we begin, a couple of words about us. RealSense is a business unit inside Intel, developing advanced computer vision solutions. My team is managing our SDK on GitHub. We are completely open source. We run on all the major operating systems and support a bunch of different languages and frameworks. So you're welcome to check out RealSense on GitHub. Just for a show of hands, how many people heard of RealSense? Nice. And how many of you tried it? Cool. So feel free to shoot an issue at us at GitHub if you have any problem. With that out of the way, let's talk about depths in robotics. So we know that computer vision can be used to solve many problems in robotics. And we at Intel believe that understanding the world in 3D is not only useful, but actually necessary to solve those problems well. Now, to give something more tangible, this is from a heavy robotics presentation at IROS. The two robots are completely identical, except the fact that one of them is operated manually by a human, and the other one is autonomous, driven by a depth camera. I'll let you decide which is which. And they're trying to pick up these beanie bags. So I hope I captured your appetite. With that, let's continue to the wide overview of depth sensing. So there's many solutions for depth sensing. One major takeaway that I want you to leave this talk with is that there's no magic bullet. There's no one technology that works best. And each of these different technologies rely on some different solution, different gimmick, and provides different benefits and drawbacks. But the three major families of depth sensing that are actually productized and selling today are based on time of flight, structured light, and stereographic depths. So first, let's get time of flight out of the way. This is a huge topic that deserves a talk of its own, and we might give one sometimes later this year. But for now, the idea behind direct time of flight is that we have a sensor, and we're sending a light pulse to the object, and we measure how much time it takes for the light pulse to get back to us, divided by 2, divided by speed of light, and we have our depth. And indirect time of flight is doing something fairly similar, but it takes advantage of polarized light and of phase shift together with some post-processing to estimate the depth data. Now, the benefits of time of flight, it's a very straightforward technology. It can scale to longer ranges. Time of flight struggles with interference from ambient light sources. For example, if you take it outdoor, outside in the sun, it can mess up the returning pulses. And for the similar reason, it struggles with interference from multiple cameras, multiple time of flight cameras. The different cameras will interfere with each other. The cost of time of flight is all over the place. You can have sensors for tens of thousands of dollars, but it's generally going down and reaching consumer, affordable levels. The main problem with time of flight is the problem of power, because in order to get a single depth frame, you have to illuminate each and every pixel, and as a result, resolution is often sacrificed to have less pixels and save on power and cost. Yeah, I'm not covering all the different, but yeah, these sensors has a lot of quirks and features, but given the limited time, I have to pick and choose. Instead of doing time of flight, other technologies rely on the concept of triangulation to calculate depths. Triangulation solutions involve two or more viewports that are offset by a constant baseline, and they estimate depths by the difference of how the object appears between the two viewports. This difference in pixels, it's called disparity, and the calculation for depths is fairly simple. One important note, interesting feature of triangulation is that if we look at the error in depth, we can see that it scales with depth squared. So what this practically means is that any triangulation-based sensor will have some recommended range of operation, and once you get beyond that range, the error will just blow up and you will not see anything useful. One way you could control that effect is by increasing the baseline, so basically making your sensor bigger, and this can definitely help. But at the same time, we want small robots, small sensors, small everything. The two main triangulation-based technologies are structured light and stereoscopic vision. In structured light, you have a projector and a camera, and they're offset by some baseline. And the sensor is projecting a fixed, hard-coded pattern into the environment, and is calculating depths based on how the geometry of the environment is distorting this fixed pattern. So basically, for every pixel in the pattern, it finds it where it falls on the image, and that way calculates the depths based on triangulation. In case of stereo, you don't project anything, but you have two viewports. And instead of using some fixed known pattern, what you do is you're actually trying to find patterns in the image itself. So you're trying to find interesting features and find where they're located in both images. And this lets you calculate based on triangulation the depth. So these two very related solutions produce very different characteristics. In case of structured light, the accuracy is usually pretty good because the pattern is very high contrast and it's very dense and textured. It's basically controlled. You're controlling what you're projecting. And the power is better than time of flight because you don't need to illuminate every pixel, just the white ones, where you have some pattern. But it suffers from the same problems as time of flight. So if you have two structured light sensors, they will definitely interfere with each other. And if you take structured light sensor outdoor, the sun will be a problem. Stereo, on the other hand, you can do without projecting anything in a completely passive way. And this means that multi-camera is a no-brainer out of the box. And power is great because you just need 2 cameras. And also, because you're relying on the features that are inside the image, the more light you have, the better. So you can take it outdoor and it will work great. Accuracy depends on, first of all, accuracy depends on what you see and if the scene has sufficient amount of interesting features. But it also depends on how well your algorithm can identify and match these features. Now, one problem that made stereo pretty much impractical up until recently is that in order to get a dense depth image, you actually need to solve a dense image registration problem, which is quite heavy in terms of computational resources. And it's not something you would generally want to do without some kind of hardware acceleration. Some solve this problem with a GPU, and there are other solutions that we'll see. So we at RealSense have a lot of experience with all kinds of depth sensing technologies. And I will use a couple of examples to demonstrate some of the points. The SR300 is an advanced structured light sensor that relies not just on one, but on several different patterns that it projects very fast to generate one depth image. What this gives is pretty high accuracy. You can see all the details in the fingers and the folds in the jacket. But where it breaks down, where all structured light sensors kind of break down, is when you take it outdoor. Once you're outdoor, the sunlight washes out all the pattern that the camera is trying to project, and even if the object is very close, you just can't see anything. Now, since we are all interested in stuff like self-driving cars and autonomous delivery drones, working outdoor is a good idea. So that's where stereo comes in. And you can see the effect is dramatic. Instead of getting just a couple of pixels of distance, now you have the entire scene mapped. This is the D400 depth cameras that we released last year. It combines characteristics of stereoscopic matching with structured light, which allows it to work well indoor, outdoor, in bright sunlight, and in dark environments. And the other cool thing about this camera is that it solves the computational barrier by having a dedicated VPU, dedicated ASIC, designed to do the depth stereo matching. So that the compute on the host platform is minimal. Using this technology, you could easily build a robot capable of autonomous navigation using the tools that we saw in the previous talks. However, if at any point the camera is blocked for some reason, it's very likely that the robot will lose tracking. This is what was mentioned as a hijacked robot problem. And one way to work around it is to integrate an IMU. An IMU is a collection of sensors containing accelerometer, which measures the total forces acting on the device at any given time, and a gyroscope, which measures angular velocity, and it might contain some other sensors. And the first thing that you can do with an IMU is you can get it into one of the well-known IMU filters. IMU filters are getting accelerometer, forces, and angular velocities, and combining them into orientation. And this way, like in this video, the camera can actually understand how it is moving. With all this data, we can now plug it into any of the open source existing SLAM solutions, and we've seen quite a few. The one we chose for this demo is RTABMap. It's a visual odometry system based on descriptor matching that also incorporates optical flow. It also can perform loop closure using a graph algorithm. It's constantly building a graph of the areas where it visited. And once it detects that it has been in certain place before, it will propagate this discovery back to correct the previous detections. So in this case, we are just moving through the cubicle area, and we're not doing anything sophisticated. This is just pretty much the camera, ROS, RTAB map, without any additional filtering or anything like that. And we're pretty quickly getting a interesting three-dimensional map of the environment, which can be quite important if you have robots that need to understand, if there's a gap between the floor and the door, or if there's some 3D structure in the way that it can maneuver around. And now, I hope you saw this point in time where it finished the loop and connected the map. This is an example of loop closure. So in order to combine and have all this running in ROS, this is pretty much the detailed structure of nodes and topics that you would need. And if we simplify, you can look at it like this. So we talked about the depth camera, we talked about the IMU data, going into the IMU filter, both feeding into RTAB map, and producing a pose and a map. And we actually have this pretty well documented in our wiki. So if you want to learn more and try this, the URL is behind the QR code. Now, this is nice, but something is still missing. I mean, we started with this very complicated problem of dense image registration for stereo matching, and we solved it by designing a dedicated hardware that is capable of addressing this problem. And then we piled up a bunch of additional computer vision modules on top of it just to have mapping, which in a way defeats the purpose. So this is exactly why, just last week, we have announced a new type of tracking camera. So this is very similar to other RealSense devices, but instead of calculating depth on board, it actually calculates SLAM on board. And instead of providing distances, it provides the 6DoF pose of the device itself. It's based on visual odometry with relocalization. And just to give you a taste, now we have liftoff. So this is the camera attached to a drone and being used as an alternative source of navigation where GPS is not available. So this is pretty much how it works. It constantly mapping the visual features in the scene and reporting back the 3D position. And once it goes down for landing, you can see the performance and the loop closure and all that. And obviously it will also work for other robotic applications, and we tried it in areas like VR. Here the drone is doing like fast forward motion and then coming back, and now we're going for landing, and that's it. So I have a couple of these devices with me here. Let me see if this will work. How do I present it to the other screen? Sorry. So this is the SR300 that I was starting with, the structured light sensor. And you can see that it does what it's expected to do. This is the D400. So this one is the one that we're giving away at the end of the talk. We also recently added the variant of D400 with an IMU. And I hope that by the end of the talk we are going to have the T265, the tracking camera here, but I don't see our demo guy. So if you're interested to see the new stuff, stick around and talk to us, and hopefully we'll have something working here in short matter of time. And with that out of the way, yeah, we can do the raffle.